Yeah.
Okay. Well, I'm sorry for.
Oh no, someone's pulled it off. Someone's started it. Better IT skills than you and me. Yeah.
Yeah, sure. I'm happy. Okay, I will mute myself. And Ian, the floor is yours.
Cool. Well, first of all, welcome everyone this morning, and thank you so much for having me. As Jaap said, I've known him for a good number of years. We met during collaborations with super yachts and sailing and commercial vessels, and you're very lucky to have one of the most experienced and technically capable people in the industry guiding you on your way. So it's a real pleasure for me to speak to you. As I said, I think I just set the scene with a little video. I like it because you'll recognize the voice, and I come from an era where Star Wars was invented, so it's a good reminder of what this is all about. No sound with the video. Now, it's a powerful video that I should credit the Conservation International for, but yeah, Han Solo's much better at speaking on these matters than almost anyone in the world for a Star Wars fan. And I think really for me, someone who from very early age was on the water as a sailor and discovered that sense of freedom that the water gave me. I think any of us who have been on the water understand the power of it, but also for me, it's a sense of freedom and connectivity that water does. It, it makes you realize how small the world is, how small a dot in time we are. And to think that we are part of the 4 or 5 generations that could trash the planet is out of the literally millions of generations that have come before us is something that we really need to take seriously. And I think your generation probably are more aware of that than mine or Jaap's. And it's to your credit that the world is changing. The people are taking a lot of background. I was at uni, God, how many years ago now? 27, 28 years ago, 30 years ago. And I actually didn't study engineering. I studied or naval architecture. I was studying economics and mathematics. And that's, something that underpins a lot of what I do now in work, but for me, and actually even in the America's Cup and the Olympics, it's that problem solving that you guys are learning today is going to be value for you, anything that you do. I went on to my first Olympics was in the year 2000. I finished university in 98. I'm impressed to imagine not many of you were born, and went on to compete in the Olympics, and things went really well there. You know, I had things went well, and I ended up winning that Olympics and got the gold in the fin class, the men's single-hander, and that really turned my life around. But maybe the thing that changed my life more was the following Olympics, which was the one of the three where I didn't get a medal. And it's probably worth touching on now just for you guys, because what I learned about there was, I guess after Sydney, you start, and I'd won in Sydney, I believe that I was talented, I guess, and that's a really dangerous and incorrect game. Yes, of course, you're born with strengths and weaknesses, but I started to believe that it was going to be some innate talent that would help me to win in Athens, which was the 2004 Olympics, and didn't take life as seriously, didn't train as hard. And I think for me, not getting a medal in Athens was the thing that's changed my life most of all. It was so painful to deal, not with losing, but with losing, having known that you haven't put in enough effort and letting yourself down. And I really distinctly remember a feeling going into the China Olympics, which is the top left of the screen there, where we won gold in China in 2008. About a week before, I remember going into the competition, and we had a training race day against all the other competitors, and we had a really good day, won most of the races. And I remember coming in, I mean, it didn't count, it was just training. I remember coming in and thinking that win, lose, or draw in that Olympics, I was not going to have that same sense that I had in Athens. We had worked so hard for the preceding 3-4 years, like every single hour of every day, with complete sacrifice of any other aspect of my life. And I remember thinking, look, if it doesn't go our way, for those of you sail know that there's luck involved and at times, and if it doesn't go our way, I won't mind. We've done enough to be the best. We might not be the case, but whatever happens, I'll be proud of the effort. And I think that's something that stuck with me. And it's funny because we all remember as kids, our parents saying, just do your best, as long as you do your best. And I remember as a kid thinking, what a load of rubbish. I want to win. It's not about doing my best. But genuinely, 1 week before the 2008 Olympics, it really resonated. My mum saying to me, just do your best, because it was very depressurizing. It made me realize that I had done my best, and that in itself was very valuable. So I guess those two events for me were very significant. Not winning when I hadn't done my best, and going into a competition knowing whatever happens, we had done our best, and we did go on to win, but that honestly felt fine. And the same in the next Olympics, where we got a silver in a brutal last race, but we've probably been the best. Felt absolutely fine about it. I mean, a little bit of swearing and shouting at the time, but I felt absolutely fine about it in the long run because we had done our best. And so, there was a lot of things that changed me. And then I went into America's Cup and ran America's Cup race teams eventually, having been a sailor on the teams. And as you move into the America's Cup, you very much start to become involved on the engineering front. As a sailor, I learned very hard that it wasn't my skill that was going to make the difference. It was the skill of the engineers. And we see that in Formula One. Your hero there, Max Verstappen, a very talented driver, but I'm not sure he'd be winning in the other cars. And so it's the same for me as a sailor. You maybe without so much talent as Max, but you realize that it's about the engineers and you have to respect. And so when I became more involved with managing the team, a lot of my effort turned towards the engineering front, which I found really fascinating, and it's what's led me into Artemis Technologies. Let's move a slide on just to talk a little bit about Artemis Technologies. So Artemis Technologies was founded in 2017. I was in that picture on the top right. I could boast and claim I was pushing a couple of 100 watts out at that moment, but I'm not sure it's true. But it certainly wasn't a whole heap of energy. There was three others with me, 4 of us putting out a couple of 300 watts, but that boat was going up to 50 knots. And that, as Jaap said, was really the epitome of efficiency. I mean, the old boats, the old monohulls, were efficient in their own way to the rule that was given, but they didn't have that same level of kind of speed that came with it and technical advantage. It was clear there was something there. There was something special about the level of efficiency it got to. Also in 2017, the IMO, the International Maritime Organization, sent out targets saying they were going to reduce their emissions by 2050 by 50%. It sounds out of date now to do that, and I'm sure you guys are working hard to be able to expedite that for the worldwide shipping industry. So, you know, there was clearly a problem. IMO were putting their hands up and saying we have a problem. We had boats that were incredibly efficient. They were not efficient economically. They were efficient in terms of that boat cost the campaign, you know, over 100 million sterling to do. It wasn't necessarily efficient economically, but it was efficient technically, and it had an opportunity. So I'm going to play a little video that it was my little story. I started telling people about how efficient these boats were, which generally got told what a load of rubbish, and then people thought about it and thought maybe not. So I'm going to play the video, and you guys as students can think. Now there's the odd caveat that this doesn't always work, so you guys can see where the fault in my logic here is and write it in the chat. As I say, you can write in the chat why you think that will or won't work. Our real dynamic high fidelity modelers say that you've got to think about wind shear. And what's the opposite of wind shear? When your air's not moving, but the water is, you can't assume there's no shear. So that's the kind of clue to why that may not be always true, but there you go. So where are we today, Artemis Technology? So we took that concept. We were a team of quite talented engineers, and so we started as a consulting business. Some of the experience of the people working with me then came from a real variety, which was essentially the America's Cup. It went from teams of 40 naval architects and structure engineers turned into design teams of about 80. And all the people that came in were more on autonomy, systems, electrical engineering, and mechatronics. And so the skill level of our group that came out of that Cup in 17 was more around dynamic modeling, control systems, and control system in the loop simulation. So that was really our background. So now this is quite out of date. We're about 150 people. Yap's been to our offices. We're growing fast, and we still work in the space of as a consulting business. We still work a lot on wing sales, but we now bring our own product to market. Our real skill back in those days, though, what do you have when you leave an America's Cup team? Because there's not a massive second-hand market for America's Cup boats, that's for sure. So there's not real value in the boat. Where there's value is, and it sounds a little bit cheesy, but the really thing you have is a way of thinking, and a way of thinking that's been imposed upon you by the rules of the America's Cup. The America's Cup, for those most will probably know it, but it's a competition where they change the rules very regularly. And each time it could be a monohull or a multi-hull or over wing sails or double membrane sails as we have this time. So the kind of physical geometries change quite considerably, which means you need to have and the most significant thing there is you only get one real chance to build the boat because you use most of the time up for design and building. So you know pretty much by the time you launch your boat, you've won or lost. It's very rare that you win for any reason but having made the fastest boat in the America's Cup. I don't think it's ever happened. So you've really won the race before you've launched the boat. Ironically, you've won it before any sailing is ever done. So where have you won it? Well, you've won it in the digital world. You've won it in the world where you are trying to optimize different design candidates to create the fastest digital candidate, which you then go on to build. The digital space can be expressed in lots of different ways, and I'll talk about that in the next slide. But the key to the digital space is, yes, the models. The models are important, but the real key for me is understanding what winning is and trying to express that digitally. And I think that's a lesson for you guys can take forward into anything that you put your, great intelligence and ingenuity to. First of all, you've got to decide what winning the race is. Well, it sounds simple. In an America's Cup race, it's crossing the line ahead of the other one. But then, of course, you've got lots of variety of conditions. And then you have to realize there's a second boat. So there's a game theory element. It's like a boxing fight. If someone's really small and nimble, the big, stronger guy can't hit them. So it's not necessarily about being strong. So first of all, you've got to try. And then once you've worked out what winning the race is, you've got to express that in a language that can be used systematically to assess candidates. And that's really, really critical. So if you want to decide to build a new eco ship, first of all, you've got to understand what winning the race is. Well, it's probably a business model. It's probably a business model for the shipping companies. To a point, it's emission saving, of course, too, which you're trying to value at a certain amount. I like your ship there. Come on the screen. So first of all, you've got to try and understand what winning the race is. Then you've got to try and express what winning the race is in a numerical sense. Because if you can't express it in a numerical sense, there's no way that you can systematically assess things. So then, of course, you can use, now you've got winning a race in a numerical sense, whatever your race is, you need to try to build up models to assess your ability, to represent your boat in this case, or frankly, whatever your product you're bringing or your solution you're bringing, you've got to try and build that up. Some things can be built up really simply, and other things are more complex. Some things involve humans, a part of the total machine. So you've got to have humans in the loop of the simulation. Some things have hardware that needs to be characterized, or hardware that's really hard to characterize. The classic there is always described in Formula One is the tires. They're not very good at being characterized. The problem, as I describe it, of tires against concrete is very high fidelity. It's very difficult. It's really down on the molecular level of how it grips. So modeling it's very hard. So sometimes you need to actually have hardware in the loop. You have to simulate it with something really physical. Sometimes you need to have subsystem tests that do characterize models so they can be expressed. Then you need to have real world testing to validate this stuff and to improve those models. And obviously, sometimes you can use fundamental academic research. You can just look up other people who've done this work and come up with these answers and use models. And all of these things come together to represent your physical body. And then you have the social economic factors. As I said, often winning a race is going to be someone wanting to buy the product. Because I went to a talk once from Elon Musk before he was too famous with Tesla, because I certainly wouldn't get invited to a talk now, when I was in San Fran, and he said, you don't change the world if no one buys your product, and that was a classic. So you've got to think what has to make economic sense. So the socioeconomic factors need to be in there. You need to build the model, the socioeconomic factor. But the key, this diagram's trying to illustrate here, is everything needs to be able to talk. Everything needs to be able to be expressed in one language. You can have factors in there that are completely qualitative, completely subjective, but they can still be given as factors. And my philosophy has always been build the full picture, have blocks in there that can be known to be very inaccurate. You can have blocks of information in your models that are a factor of one. And the factor of one means I don't know anything. I know it's important, but I don't know I don't know enough about it yet, or I haven't got the time to put effort into it, but I know it matters. I know it has an effect. So I'm going to have a block in my model that says it has a factor of 1. It passes through with no influence, but I'm putting it for later, giving it to a research department, giving it, you know, something I need to return to. The key is have the full picture and always try and build on what the full picture is. So we did that and we came up with this. So we were looking for areas of decarbonizing maritime where we based it purely on the middle on the right. We based it purely on a business model. So the first thing we express is the business model of a potential customer in it for any kind of product. The business model for that customer has to add up to a clear decision that they would be willing to buy your product and would make more money if they buy your product than they buy someone else. Now that's quite difficult sometimes in decarbonizing technology, and the wing sails is a classic example. When I haven't looked at this in a couple of years, so don't deflate anyone who's looking at it, but I looked at it, and we continue to do work on other people, and I looked at it from a payback in years for ships. When you really start to model it on the routes around the world that are done, I would love to see more wind use on ships. I mean, I'm a sailor and I'm passionate about decarbonizing maritime, and most maritime is still done by big ships out in the ocean, the most pollution. But when you look at the economic model, the payback time is long, especially in such an inflationary world. It's really hard to expect ship owners to do that. So we really ended up looking at a number of different areas and ended up quite, I wouldn't say massively niche, because 1/3 of the world's maritime emissions come from domestic maritime, and certainly a lot of the health implications come from domestic maritime. But we came quite niche in terms of high speed domestic maritime, commercial. And the reason for that is because the business model for the person, say, using this vessel here as a general workboat in a port, doing 100 miles, 80 miles a day, they should choose to buy this vessel over a diesel ship. They make money out of doing that decision. It's smart for them to do it. Now, the other benefits there, by far the biggest of most obvious, is the fact that it's an enabling technology that allows you to operate with zero emissions, because this has a range of 60 nautical miles. You can actually use it, or it has minimal wake, or it's quiet, or it's comfortable. They're all secondary. We wanted a business model that said it is worth buying our product. And that's been the source of everything we did. So this is where we started. This is where we are now. So that boat's been out doing two-boat testing for over a year now. So collecting a lot of data, and probably the next couple of slides don't share too widely, even though don't worry, it's not too stressful. But because I know you're recording, but you know, so the reason we do two-boat testing is a little bit the legacy of our world from race boats. You know, the ocean notoriously gives you a lot of noisy data, and it gives you a lot of variety of conditions. And so it's quite hard. And you also have a load of commercial seafarers that are quite cynical about new technology. And so you need to have the exact data and on the same day, in my opinion, to convince them that it's actually viable. But huge efficiency savings and huge comfort savings pretty much is the summary. The next slide's kind of a continuation of that, but it's quite interesting because it shows this whole concept of a CapEx OpEx model for different people, because the bottom line is our e-foiler vessel. The blue line is the sister ship with the twin outboards, the one in the video that's getting tested. So and this is kind of normalizing the energy consumption to cost effectively here. So, and then we retrofitted the twin outboard engine and loaded it with the required batteries to do 30 nautical mile range. We couldn't get, we literally, we can't fit more than that. And, you know, that's already more energy, installed energy than the e-foiler has with 60 nautical miles. We just couldn't get it to go. And so we then looked at the efficiency of a boat that could do 30 miles, which we thought is the minimum viable range for a commercial boat, and looked at it. So it's about 60% more energy if it was just a floating boat with an electric engine. So as I said, then the blue line is twin gasoline outboard. The top triangle is interesting. That was a customer of ours who runs a port in India, and they do a lot of miles with their boat, but they use a steel workboat, much heavier, lower spec, costs a lot less than the blue one. The blue line's actually, it's a carbon fiber workboat. It's pretty top of the range for that kind of product. The steel boat up in the triangle is about half the price of the blue line. And so we could run the model of all four of those different solutions and see. And what was really interesting is that the green, the blue, and the triangle dot actually all came after about 5 years to about the same business model. It wasn't a whole lot different. The electric one couldn't do most things. It wasn't able to do the range. But in terms of economics, it was pretty similar. And equally, so was the blue line and the dot and the triangle, which kind of suggested it made sense. It made sense for different companies to buy varieties of different boats. There's no, you know, buying a high spec carbon fiber workboat made sense. Buying a steel, you know, inefficient workboat made sense to others, which was, you know, really quite interesting. The only one that jumped and made a real difference when you were doing a significant mileage a day was the e-foiler. So we're trying to maximize the investment that we've made. As a company, we invested, you know, we will have by the end of next year invested near on 100 million euros into this technology. And so it's really important for us to maximize that investment over a variety of different use cases. Maritime's always really struggled, as I'm sure you guys have learned a lot and grapple with that. There's a big variety of use cases. Aeroplanes are easy. They generally go from A to B. They don't do many different things. You know, they don't crane boats. They don't do pilot operations. They don't do wind farm operations, where they need all these different valves, different top hats, as we call them, different customer requirements. Maritime has a real variety of use, and that's been hard for maritime. It's made it very hard to invest in new technologies. And so, you know, not unlike, say, Damen with their modularization, we're trying to use that approach where you try to maximize the investment you have made into multiple different products effectively. And, you know, that platform approach is very known in automotive too, where famously a VW is the same as your Porsche, but you just pay a lot more for your Porsche. So that platform approach is something we do, and as a result of that can have a large product range, which I'll kind of finish with and show you at the end where we're going. But I think the key for us is you've also got to know where your products don't work. I can't be so kind of a slave to being systematic, a slave to the models. If the models tell you your product isn't right, then you shouldn't be going there. I'll give you an example. We have a lot of wind farms in the North Sea between our countries. And so the UK's got a huge wind farm, as is Holland, market. So we look at variety of lengths of wind farm from shore or from harbour, really, because that's where they go for the wind farm support vessels. And if you take 3 vessels, you take a standard vessel today as efficient a fast cat as you can. You take a electric version of that, and you take our e-foiler vessel and you look at the wind farms in the North Sea. If you take any wind farm inside 10 nautical miles from shore, economically, the cheapest is a diesel, because over the 5 years, which is the typical contract time, a diesel's cheaper. Doesn't have the batteries, in our case, doesn't have the hydrofoils, and it's a cheaper solution. If you go between kind of 10 and 12 miles offshore, the diesel is still the cheapest, but the under 12 miles, an electric fast cat is actually cheaper than the e-foiler vessel, because there's not enough miles to pay for the extra cost of the foils and the complexity of the autonomous system. So for about a 12-mile offshore, if you wanted to decarbonize, the cheapest is diesel, but if you wanted to decarbonize, the cheapest would be to put batteries and do a conversion of an existing boat or build a new electric vessel. So we have to put our hands up. We have to say when our product is not right as well. And that's in the near shore. The good news is 85% of wind farms are outside that, and certainly all the new ones are. You start going beyond 12 miles offshore, the electric vessel can no longer have a viable range. But actually, about that point, it also stops being the most economical solution. From 12 miles on, the e-foiler starts getting cheaper than diesel over a year. And you include the, it takes, at that point, it's right on the crossover, it takes more than 5 years to be the cheaper solution. And then as you get further and further away from shore, as you do more and more miles, as it says at the top, high speed and long range, it starts to become more and more economical. And then if you're talking about wind farms about 25 miles offshore, the e-foiler vessel offers significant savings to a wind farm operator compared to using a diesel vessel. It becomes the right economic choice as well as the right environmental choice. Now, for those of you who are experts in this industry, will probably be saying, look, it's not as simple as that, and it isn't, because the fuel is currently paid by the developer, the owner of the wind farm, or and the boats are often owned by charter companies. So there's much more complexity, but as a total business model, that becomes something. But the key is say where you're also not good. The other thing we don't do is we don't produce boats to the markets on the right there, leisure and what we call service vessels. Now, the reason for that is twofold. One of them is kind of technical, is we don't know much about leisure and services. My feeling on leisure is it's a personal taste, it's not our expertise. Service vessels, I certainly don't know anything about the gun on the front there. So as a company, we don't have the knowledge there. But I think there's a kind of slightly more philosophical point that you could argue that the industries on the left are necessary for they're necessary for us as a society. You know, you have to go and service your wind farms, you have to commute to work, whereas leisure activity, there's not that decarbonizing to a private boat. That being said, we're not totally self-righteous. I mean, we produce technologies for other people in those sectors, so we're a subsystem provider. We're a technological solution. It's not really I'm not really being a value judgment here, but there is still that element for us as a company. Our brand is around decarbonizing maritime, and if and it's important to us, and so to decarbonize maritime, we need to concentrate on maritime that is necessary. Just to give you that flavor, therefore, of what does that mean? What can you produce, therefore, as a product range? You can see how it starts to really grow as a market size when you use this approach. We have a small platform. We have a medium platform at 24 meters. We've actually now got an intermediate platform. I think it was just because it was IP that sticks to my initials. They will call me that, which is around at 20 meters. So there's a variety of products that can come out. The key here for us is we're always trying to be classified and coded. We're not a leisure boat. We are a boat that passes the code, and we're the first. The Maritime Coastal Agency class us as a workboat. Our prototype, that's the first time an electric foiling boat's ever had that. We can operate as a commercial entity here using these vessels. That is, as you guys well know, I'm sure, non-trivial to get through. So, you know, I hope that you in the future are going to see a lot of these products out there. As I said, as always, Elon Musk said, you don't change anything to the environment if people don't buy your product. So we've got to get out there. We need to make our product better and better. And so one of the reasons I love working with Jaap is he has access to all your very talented people over there in Holland who would love. And it's much easier to persuade Dutch people to come to Belfast because the weather is not that much worse in Holland as it is in Belfast. So I hope, I'm going to get to meet a few of you in person and encourage you all to try and come and work for Artemis Technology. So thank you for your time this morning. And I did see a few questions go in. Yep.
Thank you very much, Ian. A great presentation. I've seen some of it already, but the personal notes you made in the beginning were new to me, but they fit you. Don't do anything half. If you do it, go for it. Be prepared. And that's exactly what Artemis is doing, not just building a prototype and trying to scrape some money to build the next prototype, but get the right funds and really do it on a scientific way. By the way, it reminds me to one of my trainers when I was an oarsman as a student. He said, although the races are in Amsterdam, we win them in Delft during training. Exactly the same.
Too right.
But by the way, the audience is not all students. It's partly students, but also old people like me, but who are also very interested. I saw a question from Luigi Francesco Minerva, and the question fits his job. He works at Maritime Research Institute Netherlands in Wageningen, and his question is, what are the topics where Artemis Technology feels that their models still need further research? And then he means possibly hydrofoils. Any help needed from Wageningen?
Yeah, I think we have quite a good capability in high fidelity modeling. So we can run our control systems, the exact control systems we run on the boat through CFD, doing turns, takeoffs. I think where our low fidelity modeling simulates, you know, we're not, I wouldn't say we're 100% satisfied with some of our ventilation models. You know, we have to run kind of almost probabilistic models to, you know, around pressures, obviously not purely probabilistic, but to try and give the appropriate effect on performance. So I think there's elements there around surface effects, which is always a challenge. I think probably uniquely where we have strength, I think uniquely, but your university colleagues might spark up, is this ability to rapidly prototype in high fidelity. So by that I mean control systems. So actually have real control system in the loop simulation in high fidelity. So we don't have that many assumptions, therefore. When we can take side on gas and we can run the control system through high fidelity. So I think, you know, we have quite a unique capability to roll model-based controllers through high fidelity, which is quite kind of a simulation truth that's quite useful.
Okay, thank you. A question from Timo Rodemond. Why are the larger vessels multi-hulls and the smaller ones monos?
Yeah, that's a pretty complex one. It's simply around the structure of the foils, and just as you go smaller, the span is less, obviously, on a smaller vessel, and one vertical strut is enough to support it and not get the deflected foils near the surface. As you get beamier or bigger in general, you need more vertical struts for a sensible kind of choice of wing structure. It doesn't, unlike people seem to think that two hulls is in somehow going to make you more inherently stable, but when you're up in the air, the hulls are doing nothing. It's simply about the span of the foil that gives you your roll control authority. So you could have an aeroplane style long thin wind, but our challenge, unlike an aeroplane, is the bending. And we are quite near, obviously where the water is becoming air, and we're very, very near the surface effect. So we need to avoid that. So we don't want to be we want to fly high to reduce weighted surface on the verticals, but we can't be too near the surface with the horizontals. So bending becomes an issue. And so and draft is an issue, but you can't just bend it down in static because draft is a challenge. So it gets to a point where having more than one vertical becomes sensible choice. So it's not massively, it's not a super clever answer that, but it's the truth.
Yeah, it sounds logical. Right, thanks. Jay Brandt asked the following question for the CTV type vessel. How do you deal with the pushing capacity required to stick to the boat landing?
Yeah, it's a really good question. And that's probably been one of our bigger challenges. So the answer is we carry additional power that we don't need to fly for the bollard push maneuver. So our 24-meter CTV is a 4-engine vessel versus a twin engine on the same as a ferry, and you carry that. Now, in terms of what I call parasitic drag, so pulling the extra drivetrains through the water, which is a testimony to the design of it, is an incredibly low additional drag. It's about 0.4% for us to carry the additional pods underwater. Now, that isn't the part, as I said about business modeling, there's additional bill of material costs. So it's not a positive from a business point of view, but it, you know, as the question suggests, it's a necessary requirement to have a certain thrust. And we do not simply brute force it. You know, we have ongoing projects around autonomy in the bollard push maneuver. So that one thing is but we've also got the ability in high fidelity to model the friction, the waves, multi-object wave interaction, wind interaction between, say, wind farm and vessel. And this is a great place where we thought we were going to be all clever and be able to solve things. And all the captains said to us, thrust is really important. And we thought, nah, they always just put the throttle down and they don't understand. But our modeling now confirms that thrust is really important. And so we have more thrust specifically for the bollard push.
Okay. Michael Plus asked a question. Windmill service boats can with fuels be more pleasant to passengers. However, the service limit is probably the transit situation at the windmill, apart from fuel saving. And now he writes, pitching is reduced. However, the wave sensor is vertical, causing a short signal, meaning more pitching than when horizontally oriented and gradually getting more clearance. Michael, maybe best is to unmute yourself because I do not really understand your question. Can you do that, Michael? No.
Well, one thing we do is measure a lot of the vertical accelerations. I think the key with flight control is, you've got to understand the metric you're trying to optimize. So we work a lot on comfort metrics. So trying to have, again, what is winning the race? Winning the race is more comfortable. Let's produce a metric that you can work out. So, and then in terms of how you control, I think one of the important aspects of autonomy like this is sensor fusion. And certainly we don't have one sensor, you know, at the front, or even two at the front. You have them at the front, the back, and so you have, that's your ride height data. But then of course you also have IMUs that is giving you state of the vessel, and so the key is fusing those sensors, the multiple ride height sensors and the IMU on each timestamp, and then it's about the real cleverness comes from predicting the conditions that you're in, because you know, I think there's some truth in the question. If you just start chasing your tail, you can, and you see this with the Olympic sailors in the NACRA, if they can get themselves into a state where they're setting up bad motions. So it's really important to be able to have layers in the autonomous systems that are about characterizing the conditions. So you can do that both with human interaction. You can have settings, a bit like your car suspension, but you can also have autonomy in the characterization of the sea conditions. And that's really critical, because if you're going along and you suddenly go into the wake of a big ship, or you suddenly turn a corner and you're going down waves, you need to recognize that quite fast, because the control system needs to behave very differently in different wave states. So you've got to be able to recognize that quite quickly in an autonomous way, that you're, and so the concept of characterizing the sea state is quite important. but we don't just take the key to the whole making it better or worse is understand what's the factor you're trying to optimize, and for us that's generally vertical accelerations. So it's vertical accelerations around the passenger position.
Okay, thanks, Ian. A question from Anton Groefsema. It's about floating debris. What safety measures are there to make sure that the boat stays safe when you bump into something?
Yeah, it's another really good question. You guys are touching on all the ones that our customers touch on, so that's good. So we kind of run two projects. We work a little bit with Queen's University here on both of these actually, which is the Belfast-based university. But our two major mitigations are, one is structural, and just like an aeroplane, both nose impact and then failure chains. So, there is a point if you hit a container at 40 knots where the foil will pull away. The foil then is tethered to the boat behind if you've hit a container at full speed. I think maybe unlike a normal boat, the failure chain keeps water integrity within the hull. So we see that as quite a safety improvement, yes, your foil pulls away from the vessel, but you have a watertight area which is left keeping the integrity of the vessel. So there's what happens if you do hit it, and then the obvious other way to tackle the problem is trying to avoid hitting the thing. So we had real challenges with the speeds we're going with the on the market sonar solutions. So we've been working on hardware development on the sonar side for high speed, and then I think probably almost equally challenging on the collision avoidance side is the sensor fusion, because from the early trials we've been doing here, you don't get a signal that comes in that says there's a container 100 meters away, turn left. You get a splodge of something that's come in, and you get something on the vertical on the visual sensors, and you get something on the radar, or you get something on the sonar, and the data is noisy and it's complex and it's coming very, very fast. So the real challenge for me in collision avoidance is in sensor fusion. Now, the other real challenge often, which isn't so much for us, is on the mitigation then that the vessel takes to avoid the log or the container. For us, that's quite easy. The boat's highly maneuverable. It's already got a lot of autonomy in the control. So doing an autonomous response to miss something at the last minute is actually quite easy part for us. But for larger tankers, that's an issue. For us, the real technical challenges in our collision avoidance system is the high speeds we're going on the sonar front, and on the sensor fusion from taking multiple different inputs of information.
Thanks. Anton Kistjes, also of Maritime Research Institute Netherlands, has a question. Would you consider to install a high L/D ratio sail onto your working boats to possibly improve efficiency?
Sail, as in aero sail?
Yeah.
We have certainly considered that, and we've looked at that, a long time ago, very early days, about using wind power. The real story why we took that away is we had a design candidate with a wing sail on the vessel, and it wasn't that it wasn't making it more efficient. It wasn't that it was reducing, but the wing sail was costing, let's say in orders of numbers here, was costing 1 million euros. And the e-foiler system was costing 1 million euros. The e-foiler system was paying it back itself in 1 to 5 years, and the wing sail system was paying itself back in 5 to 20 years, depending on the conditions and the route. And so as a standalone product, it wasn't standing up. Now, it didn't mean that it wasn't adding efficiency, but as a product, if you had £1 million to spend as a customer of us on an e-foil system or on a wing sail, you took the e-foil system that paid back within 1 to 2 years. You didn't take the one that took 15 years. If you had 2 million and you're incredibly passionate about the environment, you might do both. But we're pretty cynical about that at the moment. We believe that most customers are most motivated by their P&L.
Yeah, that's right. That's a big difference between sail racing and trying to make money with boats. So it's all about economics, and you know all about that. Okay, think there's one last question from Nikola Radovic. Hi, Ian. Thank you for the presentation. Can you please tell us more about the reasons to mount propulsion on the forward wing? Yeah, probably you can read it yourself.
Yeah, I mean, that was purely about the integration aspects because we're directional on the back. It's but actually on our dual engine solutions, be it pilot boats or wind farm vessels, they have propulsion on the front and back. So it's the ones that are on the front. The first one was more because it's simpler, but the ones and all our single propulsions on the front because structurally it's cheaper and less complex. So it's a overall BOM saving to put it on the front. But then we do have rear engine solutions where directional thrust is required, so wind farm vessels and pilot boats. So it's not we're not dying in the ditch around propulsion on a fixed foil. There are definitely applications where there's benefits to have propulsion on the back. There was a question about classification agencies. We always got to talk about them because they're right old pain. No, well, I mean, look, I would say the biggest learning I've been having has been in regulation and classification and how those two come together in what is really flag societies that don't have the finances of, say, aerospace regulators. They're domestic, it's different everywhere. I found that it's not the optimal model, clearly, in my opinion, compared to, say, aerospace as we go to more complex systems. I take the MCA, the UK's flag, they would, and I spoke to them recently and explained about exactly what I said to you guys today. We started with 30 to 40 structures and naval architects. We ended with 100, still 30 to 40 structures and naval architects, and 60 people in autonomy, systems, mechatronics. And flag societies don't traditionally have those skill sets, and governments aren't throwing money at them to upskill. So I think there's an issue there of centralizing some of those flags would help significantly. And in a way they do that, as the question suggests, through class societies and some of it. But I would say class societies certainly also are catching up, as we all are, to the fast-paced development. The first boat is classified with DNV. We also have classified with Lloyd's. So we work with DNV and Lloyd's on the vessels from the safety front. As I said, I think where we're going to really get caught with complex autonomous systems, be it navigationally on all our ships, is the ability to change protocols on how the vessel is controlled. Who's checking that? Who knows that? Certainly our strategy there is to be very open and almost say to them, look, if we change this parameter often on the fly, I talked about characterizing the sea state. In some ways, we are then changing our vessel. We're changing the way in which the vessel is controlled on the fly in every timestamp, because we're saying, but we try to say to them, look, don't worry about that. But if we change our battery, or we change the way our BMS works, you probably need to be involved and worried, and we should tell you. So we've been working with DNV and Lloyd's. I think I must say with DNV, both has been very friendly and positive. It's been very long. Been going for 2.5 years now, trying to get to the point where we have classified workboats that fly and are electric. And we have a team of about 8 people in regulation and classification. We started with 1, and I thought 1 was going to be more than enough, and we now have 8. So I'm certainly behind the times on learning the burdens of classification.
Yeah, welcome to the professional world. Okay, Ian, thanks a lot. This was really interesting, and hope to see you soon again. I will come over to Belfast in the coming time.
A real pleasure, and thanks to everyone for taking the time to listen today. It was nice to meet everyone.
Okay, bye.
Cheers. Bye. Yeah.